Hello, and welcome back to the live stream. So, in the last couple of streams, we added support for structs. We're now able to declare structs, create objects of them, and manipulate them. But it's been a bit annoying that we're always having to retype this struct specifier right here. So typedefs would help here. However, the typedefs are a bit tricky to implement. Let's consider an example. So when we have a variable a and a variable b, and then we can pass this expression right here. The compiler sees an identifier followed by a star followed by another identifier, and knows that this is a multiplication. Similarly, when the compiler sees int, star, and a, int is not an identifier, it is a keyword. So when it sees this star right here, this now creates a pointer of type int. And similarly, when we have like struct foo, this is also not an identifier. So we can know that we are passing a struct foo and not a thing. So this is also a pointer, not a multiplication. However, when we now do typedefs, so typedef struct foo, right here, we no longer know whether this is a multiplication or a pointer declaration, simply because this is an identifier and this is an identifier, so it could be either, right? We need to know the previous declarations that are in scope in order to correctly resolve it. So parsing typedefs is actually context sensitive in C. And this is a bit annoying. It's also the reason why I structured the compiler the way it is. So we've got the AST in this file, and then essentially what we're doing is in the compiler is while we are parsing the AST, we're also doing type checking and name lookup and so on. So we always already know that what sort of information we need in order to resolve typedefs. Now, what this means is that when we're parsing like a decal specifier list, which is like contains all the type specifiers, then we can look in the symbol table to figure out whether or not a given identifier would be the name of a type. So let's actually, I forgot to open the C standard. Let me just bring that up. And the PDF won't open. There's a race condition in my script that my fuzzy file finder that sometimes, man. Of course, this happens right now. Oh, I think. Oh. Right, now I've got it open. Now let's see whether I can bring that one over. Streaming subject. Okay. Okay, I'm back now. Sorry about that. I cannot open a new desktop while the streaming software is streaming. Okay. So debugging my setup aside, let's look at typedef. So we've got not type qualifiers, type specifiers. I think, yes. So a type specifier is a keyword or something that identifies a type. Or it is a typedef name. So we've got this list of a bunch of type specifiers right here. So those are all the type specifiers. And we also need to include a new type specifier, which is the name of an existing typedef. So where is that specified? Where type type definitions. Right, so the type def name is just a regular identifier. And then it's also a storage class specifier. So there are two things. We've got the storage class specifier typedef right here. So similar to a declaration can be static, we can also make it typedef, and then we actually declare a type and not a variable. We also have got the other half of the puzzle, which is the identifier, which is the typedef name. So let's begin by adding typedefs as a concept to the, I don't know what's the best approach. Let's parse and worry about the data structure then later on, because I don't think we can actually, like, since a typedef is just an alias for another type, and we don't want to have like full fidelity and error messages and whatnot, I don't think we need to be able to store typedefs in the AST at all. We can just, so when we see type indent, we just use the underlying type t. So we just populate the symbol table of the types with the underlying thing t. Right. So let's add a storage class specifier typedef. And then, so register static, also add you typedef, storage class typedef. Okay, so now we're passing typedef as part of a decal specifier list, which means that this is now one of the things we need to encounter. So we can be a typedef. Auto is typedef. And when we see the storage class specifier typedef, then we set its typedef to true and break. Okay. And then at the end, are there any constraints we need to watch out for typedef? Other than typedef, like I'm pretty sure we can't have typedef is discussed in 678. 678. Okay, so I'm pretty sure you cannot have like mix like static and typedef or not. All right. No. All right, at most one storage class specifier. Right. So we need to adjust this accordingly. So if we're having a typedef and already an existing storage class specifier, this is an error. Right. So we create the type according to the thing. Okay. So if is typedef. So if is typedef is set, then the storage duration must be man, this function is getting really long. So the storage duration must not be set, and the linkage must not be set, and it must not be context bar. So if storage duration or linkage or is context bar, then we log an error. Okay, And then we don't really construct anything. No, so we then need to adjust u so we can propagate whether or not we're having a typedef. Okay. It's const expand is typedef. Okay. So where is decal specifier list used? For a member decal, for a parameter decal, for a declaration, and for a global declaration. And in all of those cases, so we're getting the type. So in the case of member decal and parameters, like we don't allow typedefs in that position, so can't be typedef. For a declaration and for a global declaration. Now this is getting interesting. So we don't actually create a variable in that case. Instead, we create a typedef. What's the best way to eliminate the code duplication here? So we're parsing a decal specifier. So if this is the function body, right, we're then calling our callback. So the callback can, this callback needs to do the logic and it automatically propagates. So we're creating a variable depending on the declarator. However, if it's a typedef, then we are doing something completely different. So if it's a typedef, we're doing something, otherwise we're doing something else. And if it's a typedef, so can we return null pointer from that one? Let's see what happens. So essentially, let's just return null pointer and see what code works. Because to do add type to symbol table. That's the only side effect a typedef does. It doesn't create any actual declaration in the AST, it just adds it to the symbol table. So let's see what sort of code breaks. Right, we don't have, let's start simple, typedef int foo. Okay, so we are handling null pointers correctly, that's great. And we should also be able to do that at global scope. Yes, okay. So now we're having a typedef int foo. Okay, so let's add that to the symbol table. So in the state, we're keeping track of, right, for each scope, we have a symbol table which matches an AST symbol to a list, to a decal. We also want to match symbols to types. So want to match to a decal or to a type. We've got like this decal type thing. The type created by decal. Oh no, not struct decal. Yeah, which doesn't have me. Okay, so I think it's easier if we add a new kind of decal for that and add it to the AST, even though we never actually need it. So let's do that. We want to add a new kind of decal, a struct decal, a typedef decal. And then I need to just use. So if we're having a struct decal, we're also having a typedef declaration. Plus typedef decal. It's a basic node of kind typedef, node constructor, it has a name, and then it has a type. Constructor name type. Okay, and that's it. Like, it doesn't have any additional member, it's just the type associated with a name. So then create decal. When we're parsing a declaration, we don't return null pointer. We instead return type decal for that type. Well, so we are iterating over the declarator to get the full type, but I'm pretty sure there is already some sort of function to get the type. Declarator. Right here, get type. So we can call this function to get the type. So we're getting the type named by the typedef. State types. We've got the decal. We don't worry about that for now. What's it called? Declarator. And actually we can get you from the thing. Okay, so now we create the full type so now we're having the type, which means we can then create the typedef decal given the name of the declarator and the type. Right. Don't have position, what's it called? Pose. Okay, fair enough. So now we should see the typedef appear in the tree. And no matching constructor. Right. From name to est symbol. So name has, we also have location information here, which we don't need. Okay. So now we're creating typedef decal and have it appear in our tree. And since this is the exact same logic we're also using for the regular declaration, it should also automatically be added to the symbol table. So we can test that by doing that. Okay, maybe it's not added to the symbol table because that should create an error. All right, this is not added to the symbol table due to the way I think it is added, but since neither of those are considered definitions, we don't get an error. So let's, when we create the typedef, also make it a definition. Actually, it's always a definition, since you can't have a pure declaration of a typedef. So we can call that to make it a definition. And now we should be getting a duplicate name error. Right. So they are added to the symbol table. However, this one should be fine. Since we're creating, they're having the same type. We can see, right, this is fine. So we need to adjust the logic for name insert new decal. So if both are definitions. If they're having the same kind, which is has kind. Let's do it that way. Shadow typedef. So if it's a typedef, if shadow typedef and decl typedef and it's the same type. Then it's fine. So that should get rid of this error. Okay, so now we're adding typedefs to the tree. I mean, it's fine. It's fine. I was thinking whether we should make the second one point to the first one, but we don't actually need the AST nodes anyway. So let's commit that part. Parse typedef declaration. Okay. Now about using. So we now want to say who f. Okay. I'm curious what the compiler thinks is going on right here. All right. So it sees an identifier and thinks wants to do something like that. So let's introduce the type name type specifier. So we've got the type specifiers, and one of those is a typedef name. And typedef name is just an identifier, but it is an identifier that belongs to earlier fact name. You forgot to rename the shadow to decl. Language server, hurry up, please. Insert new decl. I'm not sure what you mean. Oh, right. Thank you. Yes. Good catch. Thanks. So now we should be getting an error because they're having different types, which I didn't actually test before. Yes, okay. Let's pretend that never happened. Okay, so a typedef name is essentially an identifier that belongs to a previous thing. This requires context-sensitive parsing. Let's see how we can pull that off. So we've got the decl specifier. Decl specifier list right here. And we want to parse a list of the keywords, a list of a struct specifier, or a typedef name. Now, and we've got a typedef name if we have an identifier, and that identifier resolves to a typedef name in the symbol table, which isn't actually possible to express as a regular Lexi rule, since Lexi doesn't know anything about a symbol table. There is a way to manually do parsing. So we're doing that right here. We're writing a function that parses things. So ideally, we would be able to just write type name production that looks in our symbol table. But we can't turn that into a branch. So we can't, like, this is a limitation of Lexi. We can't, when we're parsing, like calling scan, this always has to succeed or result in a compiler error. We can't ask Lexi, hey, is it possible that this might fail, and then continue parsing something else? Which isn't actually an issue, since it's the last thing anyway. So if you're parsing something that's neither a keyword nor a struct specifier, it has to be a typedef name, right? Oh no, it could be the identifier of the declaration already. So we need to do what I was planning on doing anyway, which is turn this whole function into a thing that we're parsing manually as well. So it's a scan production that results in a typedef specs object. That means that we get a scan function similar to this one. And here we need to do our logic. So first of all, we're getting the position. And then we need to pass a list of things and integrate those into the typedef specs stuff. So this ugly function is going to get a lot uglier, I'm afraid. So what's the best way to do that? So at this point, we essentially copy paste this entire body. Yeah, this is not nice. Let's try to refactor this out into multiple ones right here. So this one creates the qualified type based on. So we've got a bunch of state. Let's put the state into a struct. Let's call it. So let's call this one the actual list, and it contains all of those variables. So, all the previous keywords that we've seen. So we've got the linked, the storage duration, whether or not it's context bar, whether or not it's a typedef, the base type, which is either given by a keyword or by the type of a typedef, whether or not it's signed, whether or not it's short, whether or not it's qualified, and the right. Yes, this is the end. Okay. And then we have a function that essentially adds a new keyword to the thing. Add deckel specifier. Stamp list, and this is then simple deckel specifier. Simple. Let's make it a member function. Void add simple deckel. Yeah, add simple. So this adds a simple deckel specifier. And then what it does is essentially that one. So this entire logic. Let's turn you into bool, and instead of calling I'll be returning ports. We also need the current scope. So bool is global. Return false. Return false. Return false. Return false. I hate that. False. Okay. Otherwise, return true. Language server, please update.
I need to look into switching that file eventually, like splitting it up into multiple files. And then the other thing is bool add struct, which essentially just sets the base type. Base type, then we return false, otherwise we return true. Let me restart to get the language server back. Okay. Okay. So, right. Also need the state. Yeah, and let's pass the state to you for consistency as well, and I don't think this is global. And instead I can say state.current scope, state global scope. Okay. So now we've got rid of this thing. Then we also need a function that gives you the unqualified type, or actually, we just want the result type out of it. Clog type get type compiler state const, which does all of this. Instead of here, we return null pointer, and then we can just do that. Okay. And here we also return null pointer. Okay, so now we've got that structured out. Which means that our actual, right, we need to do a check right here before we do that. And let's actually do a separate function. Typedef specs get typedef specs, which does this check and then just that logic. And let's make you an optional, so we can fail at that point. Null opt. We get the type. If that is null, then we auto fail. Otherwise, we return the thing. Okay, so now we can get to the actual parsing code. So we want to parse a list of either keywords or struct specifiers. So list, let's call that result. While true. Okay, so we want to pass a keyword. If scanner.branch let's see, so scan result simple deckel specifier simple if scanner.branch simple symbol deckel specifiers. I can move you in line. Then we can return. Then we add that to the result. Add simple dot value. Okay. Otherwise, let's see. Scan result. What is the result of parsing? My language was that again. Let's just assume it's a struct deckel struct scanner.branch struct So if we're having a struct specifier, add struct, and both of those need the state, and both of those can fail. So let's get our trusty log error method back. If that fails, then we log an error. And if that fails, then we also log an error. Okay. But otherwise, if that hasn't failed, then if we can just finish the list. So if neither of those is done, then we're done with our list. And if we're getting specs, result.get type of specs, then we can just return that. Otherwise, we log an error and return lexiscan failed. Okay, and this should fully replace the existing function. Use of identifier. Oh, right. We've got a bunch of log errors here that need to translate into null pointers. So if unqualified type is null pointer, then we propagate. Too few arguments, right, get type state, compiler state, state. Too few arguments, state. No, all right. Yeah. I was thinking like static assertions. So this is not a branch condition. Where's that required? Right here. So declaration starts with a declared specifier list. Man, this is okay. This is getting really tricky. So what happens if this is simply not a branch? Then where exactly are we trying to use you? Template errors are nice. I feel like I'm missing the thing that actually terminates the instantiation. Right, this moves on to so we are trying to pass you recursively. Aha, right here. The inner declarator list. Wait, why is that a new error? Since we haven't touched that. So the inner declarator list. Why are you being used as a branch condition? Oh, hang on. I think it's inside the inner declarator list. init declarator list, parses an init declarator, parses a declarator. Which tries to... Okay, so decl specifier list. Where are being used? Right here. Right. So here we are attempting to pass you as a branch. Right, so we have to turn the decl specifier list into a branch condition. Which it isn't at the moment. Because... Okay, I think we can do... For now, we can do a little hack. So we can turn you into a branch condition by saying if you're having a KB decl specifier or a struct, then start scanning. So now it's back to being a branch condition. Let's see what. Oh. I think that's the correct incantation. Maybe that. It's a bit tricky to program without a language server. Right. So now we're getting some matching function for call to object of type parse handler. Decl specifier list. What are the candidates that you want to call? No matching conversion from too low struct decl. So we want to pass a type with specs. So we're getting a type with specs, but we're expecting a struct decl inside the decl specifier. I think maybe. Maybe that's the issue. No. Okay, so so we've got the parse handler. So we're inside scan somewhere. And this error message is really horrible. Alright, here, another matching conversion from struct decl to grammar type with specs. So apparently you produce... I don't get this error message. So we should be returning the correct thing and the parse handler. So how do we read this? So we've got the scan handler for struct decl. We're invoking the callback decl specifier list. Okay. Think you. Okay. From conversion. Struct decal. I'm from Germany. Struct decal to grammar type of spec for third argument. Struct decal. So we've got the struct decal. Why we're not supposed to be getting that one? Oh. Right here. Okay. Right, so we're recursively parsing a struct. Let's, I think, comment you out. What are you complaining about? Cool. Yeah, then that works out nicely. Yeah, it's in the afternoon for me too. Okay, so we are currently parsing the compiler. Like, what are you trying to tell me? So we've got a branch, so we don't have a branch rule, which is the sequence of a position given by a decal specifier list. Decal specifier list. Where is that? Right. I think that's right. Unused variable value. Why are you oh, right. Because temporarily disabled parsing for struct members. Okay. Okay. Right, and then the same thing. Okay. Let's make you. Okay, so I shouldn't have broken the part. So essentially everything should still work except for structs. Let's run the tests. Yeah, and then the struct part fails. Okay. This doesn't surprise me. So let's get rid of that again and try to figure out why exactly this one is failing. Oh, I think maybe. I think this could be a bug in the thing where so this one clearly it returns as pointed for struct decal. Yet it attempts to construct one because we attempt to parse as we want to get a struct decal. But what's the thing we're actually getting? It's a type with specs. So we want a struct decal, but we're getting a type with specs. Why are we getting a type with specs? We are like we're passing a struct specifier.
which is this struct, which is implemented here, which returns a struct decal. Not a, that's really odd. Like, this has to be a bug in Lexi, but I can't really see what's the issue. So where's that value getting from? Right, something to do with peak, maybe. Are we using peak here? No, we're not using peak. Wait, why are you instantiating peak? We want to peak a child. So we want to do like, that is really odd. An instantiation of function template specialization, recursive branch, grammar, struct specifier. This is wait, so we're calling, like, this is the rule that we want to pass. Then we want to finish parsing it. But then we end up, why are we ending up parsing this entire thing again inside the, oh, of course, because we are recursing. Right, the member decal recursively calls us. Right. And then that is really weird. So something to do with, we are parsing recursively a struct specifier, which in turn calls ourselves recursively, which then fails to, I think it might be something to do with that part. So we need, right, so we need a branch condition right here. So let's maybe use peak here, decal specifier list, peak, so carry decal specifiers. So if we have one of those, then we're having a declaration. But actually, okay, so there is something weird going on with Lexi. But fundamentally, this, but even if we ignore that, I think we can't do that until, so we have this function that passes the bunch of decal specifiers, which is nice and all. But it has to be a branch rule. And the scan function is not a branch. And we can't really, and it has to be a branch, it doesn't work otherwise. Because we want to be able to distinguish between, so we want to be able to distinguish between F0 and, right, this is a function call and this is a declaration. And in order to differentiate between them, we need to know whether or not the first identifier is a struct name. And this requires writing a manual thing that parses it as a scan rule, which Lexi doesn't support anyway. So even if we somehow work around the Lexi bug that we're having, we can't really make progress on the feature anyway. So I think I will just need to end the stream right here, add the missing Lexi feature that we need, and maybe figure out what the hell is going on with it. And then continue on next time, where we can just simplify the thing again. Yeah, it's a bit unsatisfactory, but I don't think we can make much progress here during the stream. So thanks for stopping by. Hope you enjoyed it, and until next week.